Have you ever just stopped and wondered how the chips inside our computers got so insanely fast? I mean, it's not just about making transistors smaller and smaller. It turns out one of the biggest, most important breakthroughs was an idea they borrowed from, of all places, a car factory.
So yeah, how did we get here? From these massive machines that filled entire rooms to tiny little devices in our pockets that can just run circles around them. Well, it wasn't just one magic invention. It was a whole series of really clever ideas, each one building on the last. And today, we're going to dig into one of the most important tricks of all, a trick that made our CPUs unbelievably more efficient.
All right, to get this, let's imagine the brain of an old-school computer is just a single, super hardworking robot. And this little robot, it's got a recipe to follow, right? That's our program. Its whole job is to do every single step in that recipe, one by one by one. And for every single line in that recipe, a robot does three things, always in the same order. First, it has to fetch the instruction from the computer's memory. Then, it has to decode it, figure out what on earth it's supposed to do. And finally, it executes the command, which is where it actually does the math, the real work.
Okay, but here's the huge problem. While our little robot is busy executing an instruction, doing the work, the parts of its brain that do the fetching and the decoding, they're just sitting there, totally idle, doing nothing. That's like having a chef who's using the oven, but the stove and the cutting board are just empty waiting. It is so wasteful. Literally 2/3 of the chip is just waiting for its turn.
So how do you fix a problem like that? Well, engineers looked out into the real world, and they saw the classic Model T Ford production line. And they thought, wait a minute, instead of one robot doing everything, what if we made a specialized assembly line inside the chip?
And that solution is called CPU pipelining. It's brilliant. Instead of one robot doing 3 different jobs, you hire 3 specialist robots. You get one robot that does nothing but fetch instructions all day long, a second robot that only decodes them, and a third robot whose only job is to execute them, keeping that calculator part of the chip busy constantly. And this, right here, this is the big aha moment. Look at the old way on the left. It takes 3 full clock ticks to get one instruction done. But with the pipeline on the right, everything is overlapped. While the execute robot is finishing instruction number 1, the decode robot is already working on instruction number 2, and the fetch robot is grabbing number 3. Now, a single instruction still takes 3 ticks to get all the way through, but, and this is the magic part, a new instruction is finished on every single tick of the clock.
What's the result? Well, in this simple 3-stage example, you get almost a 3 times increase in what we call throughput, basically how much work gets done. The part of the chip that's doing the actual heavy lifting is now busy 100% of the time, not just 33%. This is why your phone feels so snappy when you scroll. It is a massive win, and we haven't even made the clock tick any faster.
But you knew there was a but coming, right? It's never that simple. This beautiful, perfectly efficient assembly line works like a dream, as long as the recipe is just a straight list of things to do. But programs are almost never that simple. There's a catch.
So what happens when the recipe has a twist? Programs are filled with loops, with if-then statements, with decisions. An instruction might say something like, hey, compare these 2 numbers, and if they're not equal, don't do the next thing. Jump all the way back to the top of the loop. This kind of jump is called a branch, and for a simple pipeline, it's the absolute worst-case scenario.
You see, by the time our execute robot actually gets that branch instruction and realizes, oh crap, I'm supposed to jump somewhere else, the pipeline is already full of the next couple of instructions, the wrong instructions. As one of our sources so perfectly put it, the robot basically has to pull the emergency brake, The Flintstones thing where Fred puts his feet down? Yeah, everyone just stops.
This big emergency stop has a name. It's called a pipeline flush, and it's a disaster. Everything on that assembly line, all the partially fetched and decoded work, it all gets tossed in the trash. The pipeline has to start completely over from the new location in the program, which means we're back to waiting 3 whole clock cycles before any useful work gets done again. And since these branches happen all the time in real code, this is a massive problem. So the next wave of genius in CPU design wasn't just about building the pipeline. It was about figuring out how to keep it full, even when the program was jumping all over the place. And this led to some incredibly clever fixes. Okay, so the first solution was something called the delay slot. And the logic behind it was pretty simple, actually. It was like, hey, we've already fetched and decoded the instruction right after the branch, right? So instead of just throwing it away, why don't we just
execute it anyway.
So the new rule became, the instruction sitting in the delay slot, that's the spot right after a branch, it always gets executed. Always, no matter what. This kind of put the pressure on programmers to be clever and rearrange their code to find some useful piece of work to stick in that slot that needed to get done anyway. It was a neat little workaround that saved a precious clock cycle.
Now, a much more elegant fix was pioneered by the folks over at ARM, the company whose chip designs are probably in your phone right now. They noticed that most branches are really simple. They're just used to skip one or two instructions like in a basic if-then statement. So they asked a brilliant question. What if we could get rid of the branch entirely?
The ARM approach is just so much cleaner. Instead of having a separate branch instruction, they made the instructions themselves conditional. So you might compare two numbers, and then the very next instruction is something like move if greater than. The if statement is baked right into the command. If the condition isn't met, the instruction just does nothing. It becomes a dud. The result? No jump, no flush, no problem.
Now, these fixes were absolutely brilliant, and they made a huge difference. But to truly conquer the branch problem and to build the insanely complex CPUs that we have today, engineers needed to do something that honestly sounds like science fiction. They needed to teach the chip how to predict the future.
Which, of course, leads us to the final big question. How on earth can a little piece of silicon guess which way a program is going to go before it even gets there? The answer to that is the secret sauce behind basically all modern high-performance processors.
Well, the answer is this mind-bending technique called branch prediction. That fetch robot at the very front of the line, it basically becomes a fortune teller. It keeps a detailed history of every single branch the program has ever taken, and based on that history, it makes an educated guess about which path the program is going to take this time. And with modern CPUs having pipelines that are not 3 but hundreds of stages long, getting this prediction right is absolutely critical. Guess correctly, and the assembly line screams along at full speed. Guess wrong, and you have to flush a gigantic amount of work. But the crazy complex machinery that makes that prediction possible, well, that's a story for another explainer. Thanks for tuning in.